Hello. So today I'm going to talk about my favorite subject, chemistry, and how everything in the world is made of elements which are assembled into molecules and then set in motion by chemical reactions. Elements are the pure substances from which everything else is built. You can't divide an element into anything simpler, and when you put them together, you get everything. Every element is unique. Every element has its own story. But first, a little bit of my story. So I first became interested in elements about 15 years ago for a completely silly reason. We needed a table for my office. And so in English, you can make a joke about a periodic table, because in English, the word table means both a thing that you sit at and maybe you have dinner, and it also means when you write a bunch of numbers together on paper. And so you see a periodic table, that's funny in English, not in Chinese, but, you know. So as a joke, I made a periodic table. And then I thought, well, you know, I have a periodic table, I should put elements on it. So I started collecting elements. And I just kept going, and it became unreasonable, and I had too many elements. I didn't know what to do with them all. So I thought I better take a picture of everyone, and I should write a little bit about a little story. Where did this element come from? Because otherwise I'll forget what they are. So I wrote these little descriptions, took the pictures, and I made a website where I put up all the pictures and all the stories. And then just a month or two later, I got a phone call from the editor of Popular Science magazine, which is the largest circulation science magazine in the US, and they said, do you want to write a column every month about elements? And I thought, I don't know, I've never done that before, I have no idea, but, you know, whatever. So I spent the next 10 years every month writing something about some element or something to do with chemistry, basically because we needed a table in my office. That was the only reason. So that became 2 books, Mad Science and Mad Science 2, both of which are available in Chinese, which is really nice. Then I made a better website, periodictable.com. It looks nicer, better URL. And eventually I wrote a book about elements because I figured, well, I have enough stuff now. I've written enough about different elements, I could make a book. That was 8 years ago. So that book has now been translated into 25 languages, which I can't believe that. It's amazing, including Chinese, something like 6 years ago. When you write a book, you're forced to learn a lot about many things. So I learned a lot of things about elements in the process of writing this book. And I also learned a lot about myself. So, for example, iron. You know, there's not that much to learn about iron. Iron rusts. Everybody knows that. You don't have to study it. But what took me a long time to realize is why iron makes me so sad all the time. I don't like iron. And the reason is because of rust. Rust is death and dying and decay and the end of things. Every car, every bridge, every iron fence, everything that's ever made of iron is dying slowly. It's rusting away. And it's very sad. And there's a very nice song by a popular folk singer in America named Arlo Guthrie that has a beautiful line about iron in it, about iron rusting. So I'm going to play you a little bit of that song. Okay, here it comes. Okay, so there's the graveyard of rusted automobiles, exactly like in the song. Very sad. And I like that song because it's a song about a train, and the name of the train is the city of New Orleans, and that train goes right about a mile away from my house, maybe 2 kilometers from my house. And you really can get on that train, and it will take you 1,000 miles south to New Orleans. And the whole time you see rust everywhere. You know, a rusty hammer, this to me is a sad thing. A titanium hammer, on the other hand, that is a wonderful thing. Titanium is a beautiful element. It's strong. It never rusts. It will last forever. And it will be beautiful forever. These are crystals of 99.999% pure titanium grown from a gas. Just look at it. There's no more beautiful element. In fact, people often ask me, what is my favorite element? And I don't really like this question, but everyone wants to know. And sometimes I'll just say, well, titanium, because it doesn't rust, and it's beautiful, and it's shiny, and it's strong. But really, the fact is that every element has some reason why it's nice and good and beautiful. So, for example, sodium. Sodium also is shiny, right here. But that's not why sodium is interesting. What's really cool about sodium is that you can throw it in a lake. So this is some video from a sodium party that I had a few years ago, where basically I invited a bunch of people. Well, sometimes there's sound. Basically, if you throw sodium in a lake, it explodes, and it's great. And it's one of the things that's nice about it is that it's a way of sort of bringing people together and showing them the power of chemistry and what you can do if you know a little bit about chemistry. And that's fun. So I like sodium because it's a way of bringing people together. And which brings us to the next part of my talk, which is bringing elements together. Let's say we start with 4 elements. We have hydrogen, which is an explosive gas, burns very fast. We have carbon, which is diamonds or graphite. We have oxygen, which is another gas that we need to breathe, die without oxygen. And we have chlorine, which is a gas that will kill you painfully and quickly. Very dangerous stuff. What do you think we get if we combine all 4 of these elements together? Well, you get a molecule. That's what's called when you make chemical bonds between elements. And there's millions of different molecules that you could get by combining those 4 elements. Some of those are poisonous molecules. Some of them are very boring and not good for anything. Some of them are harmless. Some of them taste good. This happens to be one that tastes good. It's sucralose. Sucralose is an artificial sweetener, a synthetic chemical that tastes sweet to us. It's used in many baked goods and chocolates as an artificial sweetener. It's interesting because it's completely synthetic. It doesn't exist in nature, and yet it tastes very good to us. So here's another example of a chemical that tastes good to us. This is sugar, ordinary table sugar from sugar cane, sugar beets. It's a natural chemical, and it's sweet. But it's actually not very sweet by standards. So this is about 45 kilograms of sugar. It's 170,000 calories, 14,000% of your recommended daily energy intake. But you see the little thing on the very top. There's a tiny little dish up there. Let's zoom in on it. So this is 4.5 grams of neotame, which is another synthetic chemical. And it's the most intensely sweet commercially available artificial sweetener. That 4.5 grams is as much sweetness as the entire 45 kilograms of sugar. So how intense is that? Well, here's a comparison that I really love. Suppose that neotame were as poisonous as the most poisonous known synthetic chemical, which is VX nerve gas, a chemical specifically designed to be as poisonous as we could possibly make it. If you were to use that incredibly poisonous version of neotame and sweeten a cup of coffee with it to a reasonable level of sweetness and drink it, you'd probably be fine. It's well below the lethal dose. Because even if it's as poisonous as the most poisonous known synthetic chemical, you still don't need enough of it to be sweet enough that it would actually be likely to kill you. I think that's amazing, and one reason why I don't worry about artificial sweeteners, because they're so little used when you put them in your food that it'd actually be difficult to design one that would be harmful. So that's an example of a molecule. I find molecules very interesting, and when I think something is interesting, apparently I write a book about it. So I've written a book about molecules, which is also available in Chinese. And so let me talk about a couple of molecules. This is one of my favorite because of how useful it is in some of my other projects, and because it helps us understand how molecules work in the world. This is cotton. If you pull a fiber off a piece of cotton, a cotton plant, it's about 2 or 3 centimeters long. It's very short. So this is 5 kilometers of cotton thread on a commercial spool. All the fibers in there are still only 2 or 3 centimeters long. They're not glued or knotted or tied or anything like that. They're just twisted around each other. And if you untwist cotton thread, you can actually take it apart without breaking any of the fibers. You just untwist them and they come apart. This turns out actually to be quite a good way of thinking about the way certain polymers, certain kinds of plastics work. Plastics are made out of long, thin molecules, just like cotton fiber is made out of long, thin fibers. You can actually sort of understand how plastic behaves by thinking about the way the thread behaved. So this is an ordinary grocery bag, like you get at the store, and you can pull it apart pretty easily. It separates. When you do this, you're probably not breaking very many of the molecules. Just like when you untwist a cotton thread, you're not breaking the fibers. You're just separating them from each other because they're not really very firmly attached to each other. But if you instead pull it and sort of stretch it until it gets longer and kind of becomes like a fiber almost, you'll feel, and you should try this at home sometime, you'll feel a certain point where it all of a sudden stops stretching and it becomes much stronger. And it'll cut your fingers. It's very hard to tear at that point. That's the point at which the molecules have all become elongated and lined up with each other, and they're sort of twisted around each other, and they can't slide anymore. And when you reach that point, you'll actually feel a bounce. It's sort of a little bounciness to it. That's the carbon-carbon backbone of those long molecules pushing back at you, and those bonds are very, very strong. They're much stronger than the bonds, the forces that are holding together the polymer molecules. So it's a very nice way of seeing sort of a molecular level thing that you can actually feel. So cotton, it's made of a molecule called cellulose, and like all polymers, there's many units repeated over and over again. So this is one unit there. So what is the molecule that's repeated many, many times in cellulose? Well, we've seen it before, just a minute ago. The unit is actually glucose. It's sugar. Cotton is made 100% sugar. So why doesn't cotton taste sweet? Why can't we eat cotton? Because if you want to get the sugar energy out of it, you have to break it up into individual sugars, and we don't have any way of doing that. We don't have any enzymes in our stomach that can break up cotton. Only certain bacteria can do that. And so if you want to get food energy from cotton, you have to feed it to cows and then eat the cows. It's a form of chemical processing that we call cattle ranching. So now you've learned something. This is two kinds of cotton. One is regular cotton. The other is cotton candy. They are both made of 100% sugar. It's just the sugar is bonded together in a different way between the two. So back to sweet things. So these are four examples of non-sugar sweeteners, of high-intensity sweeteners. Two of them are natural products from plants, and two of them, the two smaller molecules, are synthetic chemicals, the man-made chemicals. And, people often ask, it's sort of an issue, are artificial sweeteners unhealthy? Should you not eat them? The fact is, most people actually prefer the taste of the synthetic chemicals. They taste better than the plant extracts. But, what people usually worry about is it healthy or not? Should I eat this? I think this is really the wrong question. It's not a question of synthetic versus artificial that you should be asking. You should really just be asking, is this a good chemical or a bad chemical, not where did it come from? The fact is that there are good and bad synthetic chemicals, and there are good and bad natural chemicals. This is an example of a bad synthetic chemical. It's sodium acetate. It's terrible, poisonous. It was used as an artificial sweetener by the Romans, and it poisoned them. It's lead. It's not a good idea. This is an example of a bad natural chemical. It's glycyrrhizin. Apparently black licorice is not popular in China, but this is a fairly popular candy in the U.S., and the taste of licorice is glycyrrhizin, and this is very poisonous. If you eat 100 grams or so of black licorice a day, which is a lot, but not impossible, for a few months, you can have irreversible liver and kidney damage, heart damage. It's very poisonous. If it were synthetic, it would never be allowed. But because it's natural, there's no regulation, and people can put as much as they want in the food. Because natural versus artificial is the wrong question. We should be looking at, was it poisonous or not poisonous? The fact is that of the 4 most poisonous known chemicals, 3 of them are natural. It's only the 4th most poisonous, VX nerve gas, that's synthetic. Nature is much better at making poisonous chemicals than we are. And the other thing to remember is that all of us like the taste of chemicals. We all love chemicals. If you like asparagus, it's a favorite of mine. I really love asparagus. If you like asparagus, those are the chemicals that you like the taste of and that you enjoy eating. All food is made of many, many, many chemicals. Some of these are poisonous, some of them are not. Some have flavors, some are for killing bacteria or fungi, whatever. Really one has to evaluate each chemical in its own right as a good or a bad thing without really worrying about where it came from. So, at the beginning of this talk, I promised you the whole story of chemistry. So we've had elements, we've talked about molecules, now it's time for reactions. And I'm going to show you somewhat random collection of different reactions that are in a new book that I'm working on, Reactions. This book is actually not published yet, but it will be this fall in English and hopefully early next year, middle of next year in Chinese. So let me tell you some reactions. This is one of my favorite reactions of all. We start with two main ingredients, aluminum powder, which is a pure element, and iron oxide, which is a compound of iron and oxygen. You mix these things together, you pour them into a concrete pot, and you light it. And then this happens. So what's happening here is that the aluminum atoms are stealing oxygen away from the iron atoms. And you're getting a lot of heat released, And the end result of this reaction is aluminum oxide, because the oxygen is moved over to the aluminum, and iron. But not just any iron. What you get is white-hot liquid iron. And in just a few seconds, you're going to see, if you watch the bottom down there, you're going to see the iron come out. So that's liquid iron that was produced by the reaction and is now pouring out the bottom of that pot. And here it is going into a mold. So why are we doing this? This is a fairly elaborate procedure and a lot of energy released. And the answer is, so this is what it looks like after the mold has been removed. And the things you see on the left and right side there are two ends of train track. This is what it looks like after it's cooled down and it's been ground and polished. And this is actually how high-speed train tracks are joined to each other all around the world. They use this chemical reaction as a way of creating enough liquid iron to fuse, not just weld together, but actually melt together two ends of train track. And when you go on a high-speed train and it's very smooth and you're going along, you don't feel any bumping, it's because all the track has been melted together into one continuous piece. So it's a very useful chemical reaction. Really, the reason I like it is because it is the exact chemical opposite of rusting. Rusting is iron combining with oxygen to form iron oxide. Thermite is iron oxide being pushed back into iron. So it's unrusting the iron, which is cool. This is another example of a metal burning, rusting very fast. In this case, lithium metal. It combines with oxygen. It's the same kind of reaction as rusting, but faster. You can actually make iron rust that fast. This is just ordinary steel wool. You can buy it in the store. If you light it, it will burn. And the reaction that's happening is the exact same reaction, slightly different mechanism, but the same reaction as rusting, just happening so fast that the heat release makes it blow up like, or glow like that. The key to burning is always oxygen. So you can do fun things with liquid oxygen. This is just ordinary charcoal with drops of liquid oxygen dropping into it, and it so flares up. A particularly beautiful demonstration of that is if you drop charcoal powder. This is a glass that's filled with pure oxygen gas. So when the charcoal falls into it, suddenly it really brightens up because it's getting more oxygen. But even the oxygen in the air is plenty to burn rapidly like that if you have a very, very fine powder. So the powder that we're seeing here is Lycopodium powder. That it was a favorite of the alchemists, the ancient magicians, and you would have a handful of it and throw it in the fire, and there's a big fireball, and the emperor is very impressed and thinks you're a powerful wizard. And really, it's actually the spores of club moss. It's a moss spore, but it's so fine that it makes these beautiful fireballs. I like this particular sequence because we got several very nice photographs to use in the reactions book. And I'm showing you a bunch of them because Lycopodium is my favorite powder, and the kid was great in the photo shoot also. It's a beautiful powder, very much recommended. So here's an example of a beautiful chemical reaction that looks like burning, but there's no oxygen involved. It's a reaction between aluminum and bromine to form aluminum bromide. But really, I'm showing you it because I think it's the most beautiful reaction I've ever filmed. And it's not really that interesting as a reaction, but it's just very pretty. And here's another very beautiful reaction, which is not burning. If there's any chemistry teachers here, you may have done this for your students. This is a reaction between potassium iodide and lead nitrate. And the result is lead iodide, which is a beautiful gold color. This demonstration is sometimes called the golden rain demonstration if you do it in a beaker because it looks like golden raindrops falling down. But it would be a very bad idea if that sort of rain were to fall on your farm, for example, because it's lead iodide, so it would poison your farm fields for generations. So really, when I think about chemistry, what I think about is fire. And that's mainly because fire is so interesting. And humans have always been drawn to fire. It's everywhere. It's even in an orange peel. Look at that. I mean, just you get an orange peel and squeeze it, and you get a beautiful fireball. The best fire, of course, the best chemical fire, is what in my reactions book I refer to as the ancient Chinese art of chemical arranging, which is, of course, fireworks. Fireworks are just different chemicals, gunpowder, flash powder, stars with different elements for color, arranged just right, carefully by a master, you get things like this. And, you know, this is chemistry. This is what chemistry is about. It's this beautiful explosion of fire and beauty, which we see everywhere around us, but quite literally in the art of fireworks. Thank you very much for coming to see what I had to say, and thank you.